Hello, everyone, and we are back at it. More u-substitution. And we're going to look at a few more examples because now you know how to do indefinite integrals, definite integrals, and just want to show you a few more techniques and practice with this. Okay. First one. So what's the area under the curve from 1 to 3 of this function here? Now, a bit complicated, and I could write it out, maybe simplify it, but what I do see right away is that the derivative of x squared plus 1 would be 2x. And that 2 is okay because we can account for that. So let's use u-substitution. Let's let u equal x squared plus 1. And then du would be 2x dx. So we can rewrite this integral as u squared du, because we would have the x squared plus 1 squared, the x dx, and then the 2 we can account for by just putting a 1/2 in front. So then I can write 1/2 the integral of u squared du. Now just be careful because, again, the thing with doing definite integrals is there's two techniques. One is you either replace the bounds in terms of your new function u, or you keep the bounds, but you have to re-substitute x back in. Because again, these bounds are meant for the function in terms of x. Where we're looking at a new function, which this is a new function, u squared du, it wouldn't be able to, you can't just look at it on the same interval. That's not going to give us the same area under the curve. So let's see, if we first do the integral of this, which would give us, and we'll do it to two approaches, we would have u to the third over 3, and all of this is 1/2. Okay. And then we'd be evaluating, if we stuck with u substitution, replace the bounds in terms of u, well, if we plug 1 into this, 1 squared plus 1 will give us 2. So we'll be looking at from 2, and we plug in 3, 3 squared plus 1 would give us 10. We'd be looking at it from 2 to 10. In which we get here, 1/2 equals 10 to the third. Well, let's make that a 1/6. 1/6 equals 10 to the third minus 2 to the third, which is 1/6. 10 to the third would be 1,000 minus 8, which is 992 over 6. If we did the second method of replacing x back in, well, then we would be the 1/2, but instead of u, we're going to replace it with x squared plus 1. And all of that is over 3, and all of this is, well, the u is being cubed, this is being cubed. And then we can keep the bound from 1 to 3 there. Okay. So it's the integral, which is u to the third minus 3, but I replaced it back with x, which allowed us to just keep the bounds 1 to 3. In which, if I evaluate this, bring that 3 in front, it would be 1/6, 3 squared plus 1 cubed minus 1 squared plus 1 cubed, which notice how I'm going to get 1/6 equals 10 to the third minus 2 to the third, same thing I had there, which will, of course, give me the same answer in the end. And don't forget, if you're never sure on definite integrals, and if you can use a calculator, why not check it? So math function integral, and it would be 1 to 3 of x squared plus 1, and all of that squared dx. We get an answer, and hopefully, if we did 992 divided by 6, we get the same answer, so that's good. So there's your first example, a little recap from last lesson. Let's look at another one. So look at this one here, x plus 1 over x plus 2. Bit more complicated, but we can evaluate this. So let's let u equal x plus 2. And maybe you're like, I don't see how that's helping this, Ryan. It's a little tricky here. What du would then be would just be dx. How do we rewrite this same integral? Well, then that's equivalent to writing the integral. Well, u is going to be on bottom. And typically, I like u on the bottom because the integral of 1 over x is natural log of x, the absolute value of x. So I like using u on the bottom because the natural log comes in handy. It helps us solve a little bit easier. Now, how's the top? We can't just put, well, we have the du there. There's the dx. But how do we write x plus 1 if u was x plus 2? Well, notice if u is x plus 2, we could say u again. Well, that's x plus 2. But if we wanted to be plus 1, we would just have to minus 1. Right? U minus 1 little side note, is the same as saying x plus 2 minus 1, which is x plus 1. Now, again, you're like, okay, I don't see how we were able to integrate this now. Well, we can rewrite this by breaking apart the fractions and writing it as u over u minus 1 over u, and all of that with respect to u, in which that's the same as just doing 1 minus 1 over u du, and therefore the integral of this will give us u minus the natural log of the absolute value of u plus c. Then replacing u back in, we'll see that the answer here is going to be x plus 2 minus the natural log of x plus 2, absolute value, plus c. And there's your answer for that integral there. Okay. And then the very last one, what about negative 1 to 1 of 5 over x minus 3? And I show this example on there because the x minus 3, since it's to the first power, and I don't see how u-substitution would help us here. In fact, you don't need to use u-substitution always. Right? There's no need for u-substitution here. If you can do integrals without it, do it without it. U-substitution is just a technique that allows you to do a little bit more complicated ones. I can bring the 5 out in front and go 5 from negative 1 to 1 of 1 over x minus 3 dx. And what that integral is going to be is the antiderivative of 1 over x minus 3 is going to be the natural log of the absolute value of x minus 3. Because again, the derivative, a little side note, the derivative of natural log of x minus 3 is equal to 1 over, and this is for all logs, the natural log of the base, which the base here is e, times the function itself. Which notice natural log of e just goes to 1, so I get 1 over x minus 3. Okay. So there's the antiderivative, and we're going to evaluate from negative 1 to 1. So what we'll get here is 5 times the natural log of 1 minus 3 minus the natural log of negative 1 minus 3. Okay. And then, because these are absolute values, this is just the same as saying natural log of 2 minus the natural log of 4. And I think that's all we can do here. And let's check our answer, make sure we did it correct. So if we did, let's do the integral, math integral, negative 1 to 1 of 5 over x minus 3, make sure that's in parentheses, dx. So that represents the area under the curve as a decimal. And let's see if we get the same thing here. 5 times the natural log of 2 minus the natural log of 4, and all of that in parentheses. Very good. So we do get the same thing. So there it is, a little bit more practice with integrals, talking about u-substitution on definite integrals, where we have the two ideas, just be careful with bounds. And then using u-substitution again for maybe more tricky integrals. And then, just reminding you, one with the natural log being the antiderivative, but sometimes you don't even need u-substitution. If you can use it, great. If there's no need, there's no need. Okay. Hope that helps. If you have any questions, make sure you stop by office hours, ask each other, email me or message me. Okay. Keep up the good work, everyone. Bye-bye.